Welcome everyone. Have you ever looked at a dataset and thought, there's no way a straight line can capture all of this? You're not alone. Real-world data is rarely linear. It bends, twists, and curves in ways that demand more than a simple linear regression can provide. That's where polynomial regression steps in. This video is your gateway to understanding how this powerful tool can help you unlock deeper insights and build models that truly reflect the complexities of your data. Here's what you can expect in today's session. First, we'll start by defining polynomial regression and why it's essential for capturing nonlinear relationships in your data. You'll learn how it takes the basic straight line of linear regression and transforms it into curves that follow your data's true path. Next, we'll compare polynomial regression to linear regression, exploring where each excels and how polynomial regression goes further when the relationships get complex. We'll also dig into the concept of polynomial degrees, what they are, how they influence model flexibility, and why finding the right degree is crucial. Too simple, and the model misses the mark. Too complex, and it risks overfitting. But don't worry, we'll guide you through the trade-offs and strategies to balance accuracy and complexity. This video isn't just about theory, it's about real-world applications. You'll discover how polynomial regression is being used to model stock prices, analyze biological growth, study stress-strain relationships in materials, and even predict climate scenarios. No matter your field, finance, engineering, biology, or environmental science, you'll see how this technique can be applied to solve meaningful problems. For those who want to build models themselves, we'll walk through a step-by-step guide. Collecting data, pre-processing it, creating polynomial features, training the model, and evaluating its performance. You'll also learn about preventing overfitting through techniques like regularization and cross-validation, ensuring your models are robust and reliable. And we're not stopping there. You'll see advanced topics like polynomial regression with multiple variables, interaction terms, and how to integrate this method into machine learning pipelines. By the end, you'll not only understand polynomial regression, but also feel confident in using it for your own projects. So whether you're a data scientist, an engineer, a student, or just curious about how to tackle nonlinear relationships in data, you're in the right place. Buckle up, because by the end of this video, you'll have the knowledge and tools to take your modeling skills to the next level. Let's dive in. All right, let's kick things off by laying the foundation, polynomial regression. Imagine you're trying to predict a trend, like the growth of a company's revenue, temperature fluctuations over the year, or even stock market movements. You start with a straight line, like in linear regression, but something feels off. The data doesn't follow a perfect straight path. It bends, rises, dips, it's complex. That's where polynomial regression comes in. Instead of forcing a straight line onto data that clearly isn't linear, we introduce curves, allowing the model to flex and adapt to capture intricate patterns. But why does this matter? Because real-world relationships are rarely simple. Whether you're working in finance, engineering, environmental science, or healthcare, many of the patterns you see are nonlinear. A simple straight line model might miss crucial details, but polynomial regression steps up, offering a way to uncover trends that would otherwise go unnoticed. So, how does it work? At its core, polynomial regression extends linear regression by adding higher degree terms. Instead of just y equals a plus bx, we introduce squared terms, cubic terms, and beyond, each new degree adding more flexibility to the model's curve. The result? A model that can track even the most complex variations in your data. In this video, we're going to break it all down. How polynomial regression works, when to use it, and how to avoid its biggest pitfalls. Because while flexibility is great, it comes at a cost. Too much complexity can lead to overfitting, where the model learns noise instead of the real trend. But don't worry, We'll cover how to strike the right balance. Now that we've introduced polynomial regression, let's move on and compare it to linear regression, so you can see exactly when and why you should choose one over the other. Ready? Let's go. Now that we understand what polynomial regression is, let's take a step back and compare it to its simpler counterpart, linear regression. Why? Because understanding the difference is key to knowing when to use one over the other. Imagine you're analyzing a data set where the relationship between the input, independent variable, and output, dependent variable, follows a straight line. That's where linear regression shines. It finds the best fitting straight line that minimizes the error between predicted and actual values. It's simple, easy to interpret, and works great when the data follows a linear pattern. But here's the problem. Real-world data often doesn't follow a straight line. Think about temperature changes throughout the year, stock market movements, or even the relationship between age and income. These patterns curve, twist, and fluctuate, making a straight line model too restrictive. That's where polynomial regression comes in. Instead of fitting a single straight line, it introduces higher degree terms, creating curves that better fit the data. So how do they compare? 1. Model type, linear regression uses a straight line where y equals a plus bx. Polynomial regression allows for curves where y equals a plus bx plus cx squared plus dx cubed, and so on. 2. Complexity, linear regression is simpler, involving fewer parameters, making it easy to interpret and quick to train. Polynomial regression adds complexity by increasing the number of parameters, degrees, allowing it to capture intricate data patterns, but also increasing the risk of overfitting. Performance on nonlinear data. Linear regression works well for straightforward trends, but struggles when relationships are more complex. Polynomial regression can capture curves and bends, making it a better choice for nonlinear patterns. 1. Model type. Linear regression uses a straight line, where y equals a plus bx. Polynomial regression allows for curves, where y equals a plus bx plus cx squared plus dx cubed, and so on. Complexity, linear regression is simpler, involving fewer parameters, making it easy to interpret and quick to train. Polynomial regression adds complexity by increasing the number of parameters, degrees, allowing it to capture intricate data patterns, but also increasing the risk of overfitting. Performance on nonlinear. Data linear regression works well for straightforward trends, but struggles when relationships are more complex. Polynomial regression can capture curves and bends, making it a better choice for nonlinear patterns. Let's illustrate this with an example. Imagine you're predicting house prices based on square footage. If larger houses always increase in price at a steady rate, linear regression is perfect. But what if small houses are priced higher per square foot, mid-size homes follow a different trend, and luxury properties grow in value exponentially? In this case, a straight line approach would fail, while a polynomial regression model could adjust to these variations. But there's a catch. More flexibility doesn't always mean better predictions. A high-degree polynomial model can start following every tiny fluctuation in the data, learning noise instead of the actual trend. This is called overfitting. On the flip side, if the polynomial degree is too low, the model might be too simple, failing to capture the complexity of the data. This is called underfitting. So the real question isn't just whether polynomial regression is better than linear regression, it's when to use it. If the data follows a clear linear trend, a straight line is your best friend. If the data is curving and twisting, polynomial regression might be the answer, but only if applied carefully. In the next section, we'll explore polynomial degrees, how they affect the model, and why choosing the right degree is crucial to making accurate predictions. Too low and you miss patterns, too high and your model learns noise. How do we find the right balance? Let's find out. Now that we've established why polynomial regression is useful, let's dive deeper into one of its most important aspects: degrees. The degree of a polynomial function determines how flexible the curve is when fitting the data. But here's the challenge. Choosing the right degree can make or break your model. What are polynomial degrees? In a polynomial equation, the degree refers to the highest power of the variable. A polynomial regression equation looks like this: y equals a plus bx plus cx squared plus dx cubed plus x to the fourth, and so on. A degree of 1 is just a straight line. This is simple linear regression. A degree of 2 creates a quadratic curve, useful when the data has a parabolic trend. A degree of 3 introduces more bends, helping the model adjust to more complex patterns. As the degree increases, the equation becomes more flexible, allowing the curve to adapt more precisely to the dataset. At first glance, increasing the degree seems like a great idea. It allows the model to capture intricate patterns in the data. But here's where it gets tricky. A low-degree polynomial might underfit, meaning it's too simple and fails to capture important trends. On the other hand, a high-degree polynomial might overfit, meaning it adapts too closely to the training data, learning even random fluctuations rather than real patterns. Think of it like drawing a trend line through a set of points. A straight line might be too simple, while a super wavy line might be too specific to that data set and fail to generalize to new data. The risk of overfitting with higher degrees. Overfitting happens when the model becomes too tailored to the training data. Imagine a professor who teaches students by making them memorize every single fact instead of teaching them concepts. The students will ace the test, but struggle with real-world applications. That's exactly what happens with overfitting. The model performs well on the training data, but fails when exposed to new information. To illustrate, imagine predicting house prices. If you use a very high-degree polynomial, the model might perfectly fit every fluctuation in historical prices, but it won't generalize well when predicting future prices. So how do we choose the right degree? That's where cross-validation and error metrics come in. We'll explore these techniques later, but for now, the key takeaway is this: a low-degree polynomial, like 1 or 2, may underfit the data, missing important trends. A high-degree polynomial, like 7 or 8, may overfit, capturing noise instead of meaningful patterns. The goal is to find the optimal degree that balances accuracy and generalization. Next, we'll explore real-world applications of polynomial regression, from predicting stock prices to modeling climate data. This will help us see how different degrees play a role in real-world problem solving. Let's move on. Polynomial regression is used in a wide range of fields where relationships between variables are nonlinear. It allows models to capture patterns that simple linear regression would miss, making it a powerful tool across industries. In finance, polynomial regression is used for stock price prediction by analyzing historical price trends. Since stock movements are often nonlinear, a polynomial model can better capture fluctuations. It is also used in risk assessment, helping analysts understand complex relationships between financial variables and predict potential volatility. In engineering, polynomial regression plays a key role in material stress analysis, where engineers study how different materials respond to stress and strain. Since these relationships are often nonlinear, polynomial models help in designing safer and more efficient structures. It is also used in control systems, where it helps model dynamic system behaviors, allowing engineers to develop better controllers for complex mechanical and electrical systems. In biology, polynomial regression is applied to population growth modeling, helping scientists predict how populations change over time based on environmental factors and species interactions. It is also used in dose-response analysis in pharmacology, where researchers study how different drug dosages affect biological responses, optimizing treatments for better outcomes. In environmental science, polynomial regression is used in climate modeling, where it helps predict future climate changes based on past temperature and atmospheric data. It is also useful in pollution analysis, helping researchers understand the nonlinear relationships between pollution levels, health effects, and environmental changes. These applications highlight the versatility of polynomial regression. Its ability to capture nonlinear relationships makes it invaluable across disciplines where patterns are complex and ever-changing. Next, we'll explore the step-by-step process of building a polynomial regression model, from data collection to model evaluation. Building a polynomial regression model requires several key steps to ensure accuracy and reliability. From gathering data to training the model and evaluating its performance, each step plays a crucial role in creating a predictive model that balances complexity and generalization. The first step is to collect relevant data that exhibits a nonlinear relationship between independent and dependent variables. The dataset should be comprehensive, ensuring that it includes all necessary features, independent variables, and target values, dependent variables. High-quality data is the foundation of an effective polynomial regression model. Once the data is collected, it needs to be cleaned and prepared for analysis. This involves handling missing values to prevent errors in the model, removing outliers that might distort the predictions, normalizing or standardizing data to ensure that all features have similar scales, improving model performance. Polynomial regression requires transforming the independent variables by creating polynomial features. This means generating new features by raising the original values to a power. For example, if the original feature is x, polynomial regression will create x squared, x cubed, and so on. The choice of degree, 2, 3, 4, etc., determines the complexity of the model. Higher degrees allow for more flexibility, but increase the risk of overfitting. Once the dataset is prepared, the next step is to train the polynomial regression model. Split the dataset into training and testing sets, typically 80-20 split. Train the model using a suitable algorithm such as ordinary least squares, OLS, to find the best fitting polynomial function. Monitor model performance during training to ensure it captures the underlying patterns without excessive complexity. After training, the model must be evaluated to determine how well it predicts new data. This involves using the testing set to measure how well the model generalizes to unseen data, calculating performance metrics like mean squared error, MSE, and R squared, R2, to assess prediction accuracy, adjusting the polynomial degree if necessary, balancing complexity and generalization to avoid underfitting or overfitting. Each of these steps is crucial in building an effective polynomial regression model. Up next, we'll explore how to choose the right polynomial degree, a critical decision that determines the success of the model. Let's find out how to strike the perfect balance. Choosing the right degree for a polynomial regression model is one of the most important decisions in the entire process. If the degree is too low, the model oversimplifies the relationship, missing important trends in the data. This is known as underfitting, where the model lacks the flexibility to capture the true patterns in the data set. On the other hand, if the degree is too high, the model becomes too complex and starts fitting not only the real patterns, but also random noise in the training data. This is called overfitting, where the model learns fluctuations that do not generalize well to new data, resulting in poor performance on unseen observations. A low-degree polynomial, such as a second-degree quadratic function, may be able to capture simple curved trends, but might struggle with more intricate relationships in the data. A higher-degree polynomial, such as a fifth degree or higher, can adapt to very complex patterns, but is at risk of becoming too specific to the training data. The key is to find a balance between capturing the important trends without adding unnecessary complexity. The challenge is that there is no universal rule for selecting the right polynomial degree. Instead, it depends on the nature of the dataset and the problem being solved. One of the best ways to determine the right degree is through cross-validation, a technique that helps assess how well a model generalizes to new data. A common method is k-fold cross-validation, where the dataset is divided into k-subsets. The model is trained multiple times, each time using a different subset for validation, while the rest of the data is used for training. This provides a more reliable estimate of the model's ability to perform on unseen data and helps identify the degree that achieves the best balance between accuracy and generalization. If the model performs well on training data but poorly on validation data, it is likely overfitting, and reducing the degree may improve performance. Another useful approach is to analyze performance metrics such as mean squared error and R-squared. Mean squared error measures how far the predictions deviate from actual values, with lower values indicating better fit. However, simply reducing the error on training data is not enough, as an overly complex model can achieve a low error by memorizing the data rather than learning meaningful relationships. R-squared measures the proportion of variance explained by the model, with values closer to 1 indicating a better fit. While a higher R-squared value is generally preferred, an extremely high value might indicate overfitting if the model has too many degrees of freedom. Visualizing the model's fit can also provide insight into whether the chosen degree is appropriate. One approach is to plot the polynomial regression curve over the data points and assess whether it follows the underlying trend without excessive fluctuations. A model with too low a degree might produce a smooth but inaccurate representation, while a model with too high a degree may weave through every individual point, creating an unrealistic and overly sensitive curve. Residual plots can further help diagnose whether the chosen polynomial degree is appropriate. If the residuals show clear patterns rather than being randomly distributed, it may indicate that the model is either too simple or too complex. Choosing the right polynomial degree is not a one-size-fits-all decision and often requires experimentation. The best practice is to start with a lower degree and gradually increase it while monitoring performance on both training and validation data. If increasing the degree significantly reduces training error but causes validation error to rise, this is a strong sign that the model is overfitting and needs a lower degree polynomial. If both training and validation error remain high, the model may be underfitting, and increasing the degree could help capture more patterns. In real-world applications, selecting the right degree is often a balance between interpretability and accuracy. A lower degree polynomial is easier to understand and explain, while a very high degree polynomial may capture more details, but at the cost of making the model more difficult to interpret. In some cases, additional techniques such as regularization can help control model complexity without reducing flexibility too much. By carefully evaluating performance metrics, visualizing model behavior, and using cross-validation, it is possible to find the optimal degree that provides a good balance between accuracy and generalization. Finding the right polynomial degree is a crucial step in ensuring that a model not only fits the current data well, but also performs reliably on new data. Overfitting and underfitting are two major challenges when working with polynomial regression, and understanding them is crucial for building an effective model. Both occur when the model's complexity is not properly balanced, leading to inaccurate predictions. Underfitting happens when a model is too simple to capture the underlying patterns in the data, resulting in high bias. Overfitting, on the other hand, occurs when a model is too complex and starts capturing noise instead of the actual trend, leading to high variance. Underfitting typically happens when the polynomial degree is too low. For example, using a first-degree polynomial, which is a straight line, on data that clearly follows a curved trend will fail to capture the actual relationship. The model makes predictions that are too simplistic and does not learn enough from the data, causing poor performance on both the training and testing datasets. This is often a sign that the model needs a higher degree polynomial to better fit the data structure. Overfitting occurs when the polynomial degree is too high. Instead of learning the general trend in the data, the model starts to memorize individual data points, including noise and outliers. This leads to a situation where the model performs extremely well on training data, but fails to generalize to new unseen data. Overfitted models tend to have very low training error, but high error on test data, meaning they are not reliable for making predictions beyond the dataset they were trained on. One way to detect underfitting and overfitting is by comparing the training and validation errors. If both errors are high, the model is likely underfitting, and increasing the polynomial degree may improve performance. If the training error is very low, but the validation error is high, this is a clear sign of overfitting, indicating that the model has become too complex. The goal is to find the degree that minimizes the validation error while avoiding unnecessary complexity. Another useful approach is to analyze residual plots. In an ideal model, the residuals should be randomly distributed around zero. If there is a noticeable pattern in the residuals, such as a clear curve or structure, it may indicate that the model is underfitting and needs a higher degree. If the residuals are widely scattered or show extreme variations, it may be a sign of overfitting. The best way to balance underfitting and overfitting is through careful polynomial degree selection combined with validation techniques like cross-validation. Cross-validation helps estimate how well a model will perform on new data by splitting the dataset into multiple training and testing sets. This ensures that the chosen polynomial degree is not just performing well on one specific dataset, but is generalizable across different data samples. Finding the right balance between bias and variance is key. A model with high bias is too simple and misses important patterns, leading to underfitting. A model with high variance is too complex and captures random fluctuations rather than meaningful trends, leading to overfitting. The ideal polynomial degree is the one that strikes a balance between the two, achieving low error on both training and validation data. Overfitting and underfitting are common pitfalls in polynomial regression, but by carefully evaluating error metrics using residual analysis and applying cross-validation, it is possible to build a model that generalizes well. The goal is not to create a model that perfectly fits the training data, but one that makes accurate predictions on new unseen data. Selecting the right polynomial degree is crucial, and avoiding both extremes ensures that the model is neither too simplistic nor too overly specific. In the next section, we'll explore techniques that help prevent overfitting, including regularization and feature selection. Preventing overfitting is a crucial step in ensuring that a polynomial regression model generalizes well to new data. When a model becomes too complex, it starts capturing noise instead of the actual trend, leading to poor performance on unseen data. Fortunately, several techniques can help control complexity and improve the model's ability to make reliable predictions. One of the most effective methods to prevent overfitting is cross-validation. Cross-validation ensures that the model is tested on multiple subsets of the data rather than relying on a single training and testing split. A commonly used approach is k-fold cross-validation, where the dataset is divided into k subsets. The model is then trained k times, each time using a different subset as the validation set, while the rest of the data is used for training. This method provides a more accurate measure of how well the model generalizes and helps in selecting the optimal polynomial degree. Another approach is leave one out cross-validation, where each data point is used as a validation set while the rest serve as training data. While computationally expensive, this method provides a thorough evaluation of the model's performance. Regularization is another powerful technique to prevent overfitting by adding a penalty to the model's complexity. There are two common types of regularization: ridge regression and lasso regression. Ridge regression, also known as L2 regularization, penalizes large coefficients by adding a term proportional to the square of the coefficients in the cost function. This prevents the model from relying too heavily on individual features, reducing overfitting. Lasso regression, also known as L1 regularization, works similarly but has the additional effect of forcing some coefficients to become exactly zero, effectively performing feature selection by removing less important variables. Both methods help simplify the model and improve generalization by reducing the risk of excessive curve fitting. Feature selection plays an important role in controlling model complexity. When polynomial regression includes too many higher degree terms, the model may become overly sensitive to minor fluctuations in the data. By carefully selecting relevant features and removing unnecessary ones, it is possible to create a more efficient model that captures the essential patterns without overfitting. Feature selection can be done manually based on domain knowledge or through automated techniques that assess the importance of each feature and eliminate redundant ones. Another practical approach to managing overfitting is limiting the polynomial degree. While higher degree polynomials allow the model to capture intricate details, they also increase the likelihood of learning noise rather than meaningful relationships. A common strategy is to start with a lower degree polynomial and gradually increase it while monitoring validation performance. If validation error starts to increase while training error continues to decrease, it is a sign that the model is overfitting and the polynomial degree should be reduced. In addition to these techniques, collecting more data can also help improve generalization. When the dataset is too small, the model may become highly sensitive to minor variations, leading to overfitting. Increasing the dataset size provides the model with a broader range of examples, making it more robust and improving its ability to distinguish real patterns from noise. Another method to evaluate overfitting is through residual analysis. Residual plots help visualize whether the model is fitting the data correctly. If residuals display a clear pattern, it may indicate that the model is too simple or too complex. A well-balanced model should have residuals that are randomly distributed without obvious structure. By applying these techniques, it is possible to build a polynomial regression model that captures meaningful relationships without falling into the trap of overfitting. The key is to balance flexibility and simplicity, ensuring that the model generalizes well to new data while maintaining accuracy. In the next section, we will explore how to evaluate polynomial regression models using performance metrics such as mean squared error and R-squared to ensure the model's effectiveness. Evaluating a polynomial regression model is essential to ensure it makes accurate and reliable predictions. A model that performs well on training data but poorly on new data is not useful. To determine how well the model fits the data, several performance metrics and validation techniques are used. The goal of model evaluation is to find the balance between complexity and generalization, ensuring the model does not underfit or overfit. One of the most commonly used metrics for evaluating polynomial regression is mean squared error, MSE. MSE measures the average squared difference between actual values and predicted values. A lower MSE indicates that the model's predictions are close to the actual data points. However, using MSE alone is not enough, as a very high-degree polynomial can have an extremely low MSE on training data, but still fail on unseen data. That is why it is important to compare MSE on both training and validation datasets. Another widely used metric is R-squared, R2, which measures how well the independent variables explain the variance in the dependent variable. An R2 value close to 1 indicates that the model explains most of the variance in the data, while a value closer to 0 suggests that the model does not fit the data well. However, a high R2 does not always mean the model is good. If R2 is too close to 1, it might be a sign of overfitting, especially if the model has a very high polynomial degree. To avoid relying on a single metric, cross-validation is often used to assess the model's generalization ability. Cross-validation splits the data set into multiple training and validation subsets, ensuring that the model is tested on different portions of the data. The most common method is k-fold cross-validation, where the data is divided into k subsets, and the model is trained and tested k times, each time using a different subset for validation. This helps identify the optimal polynomial degree and ensures that the model is not overfitting to a specific dataset. In addition to numerical metrics, visualization techniques are important for understanding model performance. Plotting the polynomial regression curve against actual data points allows for a visual inspection of how well the model follows the underlying trend. If the curve is too smooth and does not capture the shape of the data, the model might be underfitting. If the curve follows every small fluctuation in the data, it might be overfitting. Another useful visualization is the residual plot, which shows the difference between actual and predicted values. A well-performing model should have residuals that are randomly scattered around 0. If the residuals show a clear pattern, such as a curve or increasing spread, it suggests that the model is not capturing the data correctly and might need adjustments in polynomial degree or feature selection. Model complexity plays a significant role in evaluation. Increasing the polynomial degree often reduces training error, but it does not always improve validation performance. This is where techniques like adjusted R-squared help. Unlike regular R-squared, adjusted R-squared penalizes excessive complexity by adjusting for the number of predictors in the model. This ensures that adding more polynomial terms only improves the model if they genuinely contribute to predictive accuracy. Another factor to consider is overfitting detection. If the model performs exceptionally well on training data, but has a high error on validation data, this is a strong indication of overfitting. Reducing the polynomial degree, applying regularization techniques, or increasing the dataset size can help mitigate this issue. Selecting the best polynomial degree and model configuration requires a combination of these evaluation techniques. By using MSE, R-squared, cross-validation, and residual analysis, it is possible to build a model that accurately captures nonlinear patterns while remaining generalizable to new data. In the next section, we will explore how to implement polynomial regression in Python, covering the necessary steps to pre-process data, train models, and evaluate performance using real datasets. Implementing polynomial regression in Python allows us to take theoretical concepts and apply them to real-world data. The process involves several key steps, from preparing the dataset to transforming features, training the model, and evaluating its performance. Python provides powerful libraries like NumPy, scikit-learn, and matplotlib, which make it easy to build, visualize, and analyze polynomial regression models. The first step is to prepare the data. This involves loading a dataset and splitting it into independent variables, features, and the dependent variable, target. In most cases, datasets contain multiple variables, but for polynomial regression, we typically focus on one or two key predictors that show a nonlinear relationship with the target. Once the data is loaded, it is important to check for missing values, outliers, and inconsistencies that could impact model performance. Data preprocessing techniques like normalization and standardization may also be applied to ensure numerical stability. The next step is to transform the features into polynomial terms. Unlike linear regression, which uses only the original input variables, polynomial regression generates additional features by raising the input values to different powers. This is done using scikit-learn's polynomial features function, which creates new columns for squared, cubic, and higher order terms based on the selected polynomial degree. For example, if the original dataset has a single feature x, a polynomial transformation of degree 3 will create new features for x squared and x cubed, enabling the model to capture curve relationships in the data. Once the polynomial features are created, the model is trained using scikit-learn's linear regression function. Despite its name, this function can be used for polynomial regression because polynomial transformation converts the input data into a format that allows the linear model to learn nonlinear patterns. The model is then fitted to the training data, allowing it to learn the best fitting polynomial equation that minimizes prediction error. After training, the next step is evaluating the model's performance. This involves using common regression metrics such as mean squared error, MSE, and R-squared, R2, to measure accuracy. A lower MSE indicates that the model's predictions are closer to actual values, while R-squared provides a measure of how well the model explains variability in the target variable. However, high R-squared values should be interpreted carefully, as an extremely high score may indicate overfitting, especially if a high-degree polynomial is used. To ensure the model generalizes well, cross-validation is applied. This technique helps assess how the model performs on different subsets of the dataset, reducing the risk of overfitting. By splitting the dataset into multiple training and validation sets, cross-validation provides a more reliable measure of model accuracy. Visualization is a crucial step in understanding how well the model fits the data. Using matplotlib, a scatter plot of the original data points can be overlaid with the polynomial regression curve. This helps in visually inspecting whether the curve follows the underlying trend of the data. If the curve appears too simple, the model may be underfitting, while an overly complex curve that passes through every point suggests overfitting. Choosing the right polynomial degree is an important part of implementation. A low-degree polynomial may not capture enough details, leading to underfitting, while a high-degree polynomial may lead to overfitting by fitting noise instead of the real trend. The best approach is to start with a low-degree polynomial and gradually increase it while monitoring performance metrics and validation errors. If the validation error increases significantly while the training error remains low, it is a sign that the model is overfitting and the lower degree polynomial should be used. By following these steps, polynomial regression can be effectively implemented in Python to model nonlinear relationships in real-world datasets. In the next section, we will compare polynomial regression with other regression techniques such as ridge and lasso regression and discuss their advantages and limitations in handling complex data patterns. Polynomial regression is just one of many regression techniques used to model relationships in data. While it provides flexibility in capturing nonlinear patterns, it is important to understand how it compares to other methods, particularly ridge regression and lasso regression, which help address some of polynomial regression's key challenges. Polynomial regression extends linear regression by introducing higher degree terms, allowing it to fit curves instead of straight lines. This makes it useful for modeling complex nonlinear relationships that a simple linear model would fail to capture. However, as the polynomial degree increases, the model can become too complex, leading to overfitting. Overfitting happens when the model starts capturing noise instead of the true trend, making it perform well on training data but poorly on new unseen data. To mitigate overfitting, regularization techniques such as ridge regression and lasso regression are commonly used. Both of these methods modify the standard linear regression approach by adding a penalty to the model's coefficients, reducing the risk of overfitting while maintaining predictive power. Ridge regression, also known as L2 regularization, adds a penalty equal to the sum of the squared coefficients. This discourages large coefficient values, preventing the model from relying too heavily on any single feature. Ridge regression is particularly useful when dealing with high-degree polynomial regression models, where feature coefficients tend to become extremely large. By shrinking these coefficients, ridge regression helps maintain model stability and improves generalization. Lasso regression, also known as L1 regularization, works similarly to ridge regression but with one key difference. Instead of squaring the coefficients, lasso regression applies an absolute value penalty. This not only prevents large coefficients, but also forces some of them to become exactly zero, effectively performing feature selection. By eliminating less important polynomial terms, lasso regression creates a simpler model that retains only the most relevant features, reducing complexity while maintaining accuracy. While polynomial regression, ridge regression, and lasso regression each have their strengths, selecting the right approach depends on the dataset and the problem being solved. If the data exhibits strong nonlinear patterns, polynomial regression is useful, but the risk of overfitting must be carefully managed. If overfitting becomes a problem, ridge or lasso regression can help by controlling the size of the coefficients and simplifying the model. Another key difference between these approaches is interpretability. A low-degree polynomial regression model is easy to understand and interpret. But as the degree increases, the equation becomes more complex, making it difficult to explain the relationship between variables. Ridge and lasso regression, on the other hand, are often preferred when working with high-dimensional data where interpretability is crucial. Choosing between these models depends on the trade-off between flexibility and generalization. Polynomial regression allows for capturing intricate relationships, but must be used cautiously to avoid overfitting. Ridge regression provides a way to control complexity without eliminating features, while lasso regression goes further by removing irrelevant predictors, making it useful for feature selection. In the next section, we will explore a real-world case study where polynomial regression is applied in finance, demonstrating how it models stock price movements and why selecting the right degree is crucial for making accurate predictions. Polynomial regression is widely used in financial modeling, where data patterns are often nonlinear, and traditional linear regression may fail to capture important trends. In this case study, we explore how polynomial regression is applied in finance, particularly in stock price prediction. Stock prices rarely follow a simple straight-line trend. They are influenced by multiple factors, market fluctuations, and economic conditions. By applying polynomial regression, analysts can model these nonlinear relationships and make more informed predictions. One of the most common applications of polynomial regression in finance is modeling stock price movements over time. A linear regression model may assume a constant rate of increase or decrease, but in reality, stock prices often exhibit trends that accelerate, slow down, or reverse direction. A second-degree polynomial, also known as a quadratic model, can capture simple curvatures, while higher-degree polynomials can fit more complex market trends. However, choosing the right degree is critical. A low-degree polynomial may not capture enough details, while a high-degree polynomial can lead to overfitting, making predictions unreliable. In this case study, a financial analyst applies polynomial regression to forecast stock prices over a 5-year period. By selecting a third-degree polynomial, the model captures short-term fluctuations while still maintaining generalization. The results show that a third-degree polynomial fits the stock price movements better than a simple linear trend, providing a more accurate representation of market behavior. However, testing the model on new data reveals that using a higher degree polynomial, such as a sixth or seventh degree, leads to overfitting, where the model follows every minor fluctuation in past stock prices but fails to predict future trends accurately. One way to prevent overfitting in financial modeling is by using cross-validation. By splitting historical stock price data into multiple training and validation sets, analysts can determine the optimal polynomial degree that balances accuracy and generalization. Additionally, regularization techniques such as ridge regression can be applied to control the size of the polynomial coefficients, ensuring that the model remains stable and does not react too strongly to market noise. Another challenge in financial modeling is handling external factors that influence stock prices, such as interest rates, inflation, and global economic conditions. Polynomial regression models can be extended to include multiple variables, allowing analysts to incorporate additional financial indicators into their predictions. However, increasing the number of variables also increases the complexity of the model, making feature selection crucial in avoiding unnecessary complexity. In real-world applications, polynomial regression is often used alongside other predictive techniques, such as time series analysis and machine learning models, to improve forecasting accuracy. While polynomial regression is useful for detecting short-term patterns and nonlinear relationships, it may not always be the best approach for long-term forecasting, where external factors and economic shifts play a more significant role. This case study highlights the importance of choosing the right polynomial degree, validating the model on unseen data, and incorporating external financial indicators to enhance predictive accuracy. Polynomial regression offers a powerful tool for financial analysts, but it must be applied carefully to avoid overfitting and ensure that the model remains robust over time. In the next section, we will explore another case study in biology where polynomial regression is used to model population growth and dose-response relationships in pharmacology. Polynomial regression is widely used in biological research, where relationships between variables are often nonlinear. In this case study, we explore how polynomial regression helps model biological processes such as population growth and dose-response relationships in pharmacology. Many biological phenomena exhibit complex trends that cannot be captured by simple linear models, making polynomial regression a valuable tool for analysis. One application of polynomial regression in biology is modeling population growth over time. In many ecosystems, population size does not increase or decrease at a constant rate. Instead, growth may start slowly, accelerate during an optimal period, and then level off due to resource limitations. A linear regression model would fail to capture these variations, while a quadratic or cubic polynomial regression can provide a more accurate representation of how populations change over time. In one study, researchers applied a third-degree polynomial regression to model plant height growth, where the initial phase of rapid growth was followed by a plateau. The model successfully explained 85% of the variance in the data, demonstrating how polynomial regression captures biological trends that simple models overlook. Another key use of polynomial regression in biology is in dose-response relationships in pharmacology. When studying how different doses of a drug affect biological responses, a simple linear model may not capture the true relationship. At low doses, there may be little or no effect. As the dose increases, the response may increase rapidly, followed by a plateau or even a decline at very high doses due to toxicity. A polynomial regression model can be used to predict the optimal dosage range where the drug is most effective while minimizing adverse effects. By fitting a second or third degree polynomial model, researchers can better understand how biological systems react to varying drug concentrations. Selecting the right polynomial degree is critical in biological modeling. A model with too low a degree may fail to capture key patterns, leading to underfitting, while a model with too high a degree may overfit to specific data points, making predictions less reliable. Cross-validation techniques are often used to test different polynomial degrees and ensure the model generalizes well to new biological data. In pharmacological studies, regularization methods like Lasso regression are also used to reduce unnecessary complexity and focus on the most important variables. Another challenge in biological modeling is dealing with noisy data. Biological systems are influenced by numerous environmental and genetic factors, leading to variability in measurements. Polynomial regression helps smooth out fluctuations and detect underlying trends, but it must be used carefully to avoid overfitting to noise. One approach to mitigating this risk is to use smoothed polynomial regression, which applies constraints to prevent excessive fluctuations in the fitted curve. Polynomial regression is also used in genetic studies, where researchers analyze relationships between gene expression levels and environmental conditions. In this context, polynomial models help identify nonlinear gene interactions, improving our understanding of how genes regulate biological processes. Additionally, polynomial regression plays a role in epidemiology, where it helps track disease spread by modeling infection rates over time. This case study highlights how polynomial regression is a valuable tool for capturing nonlinear relationships in biology, from population dynamics to drug interactions. By selecting the appropriate polynomial degree, validating models with cross-validation, and using regularization techniques to control complexity, researchers can gain meaningful insights into biological systems. In the next section, we will explore how polynomial regression is applied in engineering, specifically in material stress analysis and control system design. Polynomial regression plays a significant role in engineering, where relationships between variables are often complex and nonlinear. In this case study, we explore how polynomial regression is used in material stress analysis and control system design, two key areas where capturing intricate patterns is essential for accurate predictions and efficient engineering solutions. One common application of polynomial regression in engineering is material stress analysis. When engineers study how materials respond to stress and strain, they often observe nonlinear behavior, especially when materials reach their elastic or plastic limits. A simple linear model may not accurately describe these stress-strain relationships, as many materials exhibit different properties under varying loads. By applying polynomial regression, engineers can develop models that better reflect how materials behave under real-world conditions. In one study, researchers used a third-degree polynomial regression model to analyze stress-strain curves of a polymer material. The model successfully captured the nonlinear deformation patterns, achieving an R-squared value of 0.95, indicating a strong fit. Another key area where polynomial regression is applied in engineering is in control system design. Many mechanical and electrical systems follow nonlinear dynamics, requiring accurate modeling to optimize performance. In control engineering, polynomial regression helps develop system models that predict how a system will respond to various inputs. For example, in robotics, engineers use polynomial regression to model the relationship between motor torque and angular velocity, ensuring smooth and precise movements. In aerospace engineering, polynomial models are used to analyze aerodynamics and predict aircraft behavior under different flight conditions. The selection of the appropriate polynomial degree is critical in engineering applications. A model with too low a degree may fail to capture important system behaviors, leading to underfitting, while a model with a very high degree may overcomplicate the system, causing overfitting and making it difficult to interpret. Engineers often use cross-validation techniques to determine the optimal polynomial degree, ensuring the model captures essential patterns without unnecessary complexity. Regularization techniques such as ridge regression and lasso regression are commonly used in engineering applications to control polynomial complexity and prevent overfitting. In material science, regularization helps refine stress-strain models by reducing the impact of noisy experimental data. In control system design, regularization techniques ensure that models remain stable and do not introduce unnecessary fluctuations, which could lead to system instability. Another engineering challenge where polynomial regression is useful is predictive maintenance. In industries such as automotive manufacturing and aerospace, engineers use polynomial regression to model wear and tear on machinery and predict when components will need maintenance or replacement. By analyzing sensor data and fitting polynomial models, engineers can anticipate failures before they occur, reducing downtime and improving operational efficiency. Polynomial regression is also applied in thermal engineering, where it helps model heat transfer and temperature distribution in materials. Many heat-related processes follow nonlinear relationships, making polynomial regression an effective tool for understanding and optimizing thermal performance. For example, in electronics cooling, engineers use polynomial models to analyze how heat spreads across circuit boards, ensuring that components remain within safe temperature ranges. This case study highlights the importance of polynomial regression in engineering applications, from material stress analysis to control system optimization and predictive maintenance. By selecting the right polynomial degree, applying regularization techniques, and validating models with cross-validation, engineers can develop accurate and reliable models that improve system efficiency and safety. In the next section, we will explore common pitfalls in polynomial regression and how to avoid mistakes such as choosing the wrong degree, overfitting, and misinterpreting model results. Polynomial regression is a powerful tool, but it comes with several common pitfalls that can significantly impact model performance and reliability. Understanding these pitfalls is essential for building models that generalize well and provide meaningful insights. The most frequent issues include choosing the wrong polynomial degree, overfitting the model, underfitting the data, and misinterpreting results. One of the biggest mistakes in polynomial regression is choosing an inappropriate degree for the model. If the polynomial degree is too low, the model may be too simple to capture the real trends in the data, leading to underfitting. Underfitting occurs when the model lacks the flexibility to describe the data's patterns, resulting in high error rates and poor predictive performance. On the other hand, if the polynomial degree is too high, the model becomes overly complex and may start capturing random noise instead of actual relationships, leading to overfitting. Overfitting happens when the model fits the training data perfectly, but performs poorly on new unseen data, meaning it has memorized rather than learned the underlying patterns. Another common pitfall is overfitting the model, which is particularly problematic when using high-degree polynomials. While a higher degree polynomial might produce a visually perfect fit to training data, it often results in poor generalization. This means that while the model performs exceptionally well on historical data, it fails when making predictions on new datasets. A classic sign of overfitting is when the model has a very low training error but a significantly higher validation error. To prevent this issue, techniques such as cross-validation, ridge regression, and lasso regression are often used to regularize the model and control excessive complexity. Underfitting the model is another issue that occurs when a polynomial degree is too low. In such cases, the model does not capture enough variation in the data and produces inaccurate predictions. Underfitting is often indicated by high training and validation errors, suggesting that the model is too simple to represent the relationship between variables accurately. To correct underfitting, a slightly higher polynomial degree may be needed to introduce more flexibility while avoiding unnecessary complexity. Another major challenge is misinterpreting model results. Just because a polynomial regression model produces a high R-squared value does not necessarily mean it is a good model. A very high R-squared value might indicate overfitting, where the model is tailoring itself too closely to the training data rather than identifying general trends. Additionally, if the model includes too many polynomial terms, it may be difficult to interpret the relationship between variables, making it less useful for practical decision-making. Residual analysis is an important step in identifying potential pitfalls in polynomial regression. A well-balanced model should have randomly distributed residuals around zero with no clear patterns. If residuals show a systematic trend, it suggests that the model is either underfitting or overfitting the data. In some cases, examining residual plots can help decide whether a different polynomial degree is needed or whether additional regularization techniques should be applied. Another challenge arises when working with small data sets. Polynomial regression models require a sufficient number of data points to generalize well. If the data set is too small, a high-degree polynomial model might fit the few available points too closely, leading to misleading results. Increasing the data set size can help improve the model's stability and reduce the risk of overfitting. To avoid these pitfalls, it is important to follow best practices in polynomial regression modeling. Cross-validation should be used to test different polynomial degrees and ensure that the model generalizes well to new data. Regularization techniques like ridge and lasso regression can be applied to prevent excessive complexity. Residual plots should be checked to confirm that the model captures meaningful patterns rather than noise. Finally, models should be evaluated using multiple performance metrics such as mean squared error, MSE, and adjusted R-squared, rather than relying solely on standard R-squared values. By understanding and addressing these pitfalls, polynomial regression models can be optimized for accuracy, interpretability, and generalization. In the next section, we will explore advanced topics in polynomial regression, including techniques such as feature scaling, interaction terms, and automated model selection to further enhance predictive power. Polynomial regression can be extended to handle multiple variables, allowing for more complex relationships to be captured within a dataset. Unlike standard polynomial regression, which typically involves a single independent variable raised to various powers. Multivariate polynomial regression incorporates multiple independent variables and their polynomial interactions to better model intricate patterns. This approach is particularly useful when relationships between variables are nonlinear and involve interactions, making simple linear regression insufficient. The general form of a multiple variable polynomial regression equation is more complex than a single variable polynomial regression model. Instead of having a single independent variable raised to different powers, it includes multiple predictors and their interaction terms. For example, a second-degree polynomial regression model with two independent variables, x1 and x2, would look like y equals a plus b1x1 plus b2o2 plus c1mec1 squared plus c2o2 squared plus dx1log2. This equation includes linear terms, squared terms, and an interaction term, which captures how the two independent variables influence each other. Higher degree polynomial models introduce additional interaction terms, allowing for even more complex relationships to be modeled. One of the biggest challenges in multivariate polynomial regression is selecting the appropriate polynomial degree. As the number of independent variables increases, the number of polynomial terms grows exponentially. For example, a third-degree polynomial with three independent variables includes not only x1 cubed, x2 cubed, and x3 cubed, but also numerous interaction terms such as x1 squared times x2, x2 squared times x3, and so on. This rapid increase in complexity can lead to overfitting, where the model captures noise rather than meaningful trends. To manage this complexity, techniques such as cross-validation are used to compare models of different degrees and determine which degree provides the best balance between accuracy and generalization. If the polynomial degree is too low, the model may underfit, failing to capture important trends. If the degree is too high, the model may overfit, making predictions unreliable on new data. Another key challenge is selecting relevant features and reducing unnecessary complexity. Including too many polynomial terms can make the model difficult to interpret and computationally expensive. Feature selection methods can be used to identify the most important polynomial terms while removing redundant ones. Lasso regression, L1 regularization, is particularly useful in this case because it helps reduce the number of features by shrinking some coefficients to zero, effectively eliminating less important terms from the model. As polynomial terms increase, interpreting the model becomes more difficult. Unlike a simple linear regression model, where each coefficient represents a clear relationship between an independent variable and the dependent variable, polynomial regression coefficients do not always have straightforward interpretations. This is especially true when interaction terms are introduced, as they represent combined effects between multiple variables rather than isolated influences. One way to make polynomial regression more interpretable is by using visualization techniques. While plotting polynomial regression with a single independent variable is simple, visualizing models with multiple variables requires contour plots, heat maps, or 3D surface plots. These visualizations help in understanding how different variables interact and influence the target variable. As polynomial terms increase, the risk of overfitting becomes more significant. To prevent this, several strategies can be applied, including regularization techniques such as ridge regression, L2, and lasso regression, L1, to control the size of polynomial coefficients. Cross-validation, to compare models with different polynomial degrees and select the one that provides the best balance between accuracy and generalization. Feature selection methods to reduce the number of polynomial terms and keep only the most relevant ones. Increasing the dataset size, as polynomial models require more data points to remain stable when handling a large number of features. This type of regression is widely used in engineering, economics, and scientific research, where multiple factors influence an outcome in a nonlinear way. In aerospace engineering, polynomial regression helps model aircraft aerodynamics by considering variables like air pressure, velocity, and altitude. In climate science, it is used to predict weather patterns based on temperature, humidity, and wind speed. In finance, multivariate polynomial regression can model risk factors affecting stock prices or economic trends. By applying polynomial regression with multiple variables, analysts can capture complex relationships that traditional linear models would miss. However, careful consideration must be given to model complexity, feature selection, and interpretability to ensure that the model remains useful and generalizes well to new data. In the next section, we will explore how polynomial regression models can be visualized to better understand their behavior, using tools like contour plots and 3D surface graphs to illustrate nonlinear relationships. Visualizing polynomial regression results is essential for understanding how well the model fits the data and for diagnosing potential issues like underfitting or overfitting. Unlike linear regression, where a simple straight-line plot is often sufficient, polynomial regression requires more advanced visualization techniques, especially when dealing with higher-degree polynomials or multiple independent variables. One of the most common ways to visualize polynomial regression is by graphing the regression curve over a scatter plot of the data points. When working with a single independent variable, plotting the polynomial curve alongside the actual data points provides a clear representation of how well the model captures the underlying trend. A well-fitted polynomial should follow the general shape of the data without excessive oscillations. If the curve appears too smooth and does not adapt to the natural curvature of the data, the model may be underfitting. If the curve fluctuates excessively, bending through every individual data point, it is likely overfitting and capturing noise rather than the real trend. For multiple variable polynomial regression, visualization becomes more complex. Since the relationship involves multiple dimensions, standard 2D plots are not always sufficient. One approach is to use 3D surface plots, which show how two independent variables interact with the dependent variable. A well-constructed 3D polynomial regression model should create a smooth surface that aligns with the data distribution. However, if the surface appears excessively curved or forms sharp peaks and valleys, it may indicate an overly complex polynomial model that is overfitting the data. Another powerful visualization technique is contour plotting, where different levels of the predicted variable are represented as contour lines over a grid of the independent variables. Contour plots are especially useful for analyzing how two predictors influence the target variable simultaneously. If the contours are too erratic or highly concentrated in certain areas, it may indicate that the polynomial model is too sensitive to minor fluctuations in the dataset. Residual plots are another important tool for assessing the performance of polynomial regression. A residual plot visualizes the difference between actual and predicted values. Ideally, residuals should be randomly distributed around zero, indicating that the model captures the general trend without systematic errors. If the residuals show a clear pattern, such as a wave-like structure, it suggests that the polynomial degree may not be appropriate. A model that underfits the data will display residuals with a clear pattern, while a model that overfits may have residuals that are small on training data but large on test data. Comparing polynomial degrees visually can help select the right model. One way to do this is to plot multiple polynomial regression curves of different degrees on the same scatter plot and observe how they behave. A first-degree polynomial linear regression may be too simple, missing key trends. A third-degree polynomial might follow the natural shape of the data, while a seventh-degree polynomial could oscillate excessively. By visually inspecting these curves, it is possible to identify the optimal balance between flexibility and simplicity. In practical applications, interactive visualizations can help explore how polynomial regression models behave under different conditions. Many data analysis tools allow users to adjust polynomial degrees dynamically and observe changes in the regression curve in real time. This is particularly useful in exploratory data analysis, where analysts need to experiment with different polynomial transformations before finalizing a model. By leveraging these visualization techniques, analysts can better understand the strengths and weaknesses of their polynomial regression models, ensuring that they capture meaningful patterns while avoiding overfitting. In the next section, we will explore how polynomial regression integrates into machine learning pipelines, demonstrating how it can be automated and combined with other modeling techniques for better performance in real-world applications. Polynomial regression can be seamlessly integrated into machine learning pipelines, allowing for automated model building, selection, and evaluation. In real-world applications, polynomial regression is rarely used in isolation. Instead, it is part of a larger workflow that includes data preprocessing, feature transformation, hyperparameter tuning, and model evaluation. By incorporating polynomial regression into machine learning pipelines, we can automate the process of selecting the optimal polynomial degree, ensuring that models generalize well to unseen data. The first step in integrating polynomial regression into a machine learning pipeline is data preprocessing. Raw data is often noisy, contains missing values, or includes features that need to be transformed before they can be used in a regression model. Preprocessing involves handling missing data, removing outliers, and normalizing or standardizing numerical features to ensure numerical stability. Since polynomial regression generates additional features by raising input values to higher powers, proper feature scaling is essential to prevent some terms from dominating others. Standardization, where values are transformed to have a mean of 0 and a standard deviation of 1, helps prevent issues where higher degree terms become disproportionately large. Once the data is cleaned, the next step is feature transformation. Polynomial regression requires generating polynomial features from the input variables. This is done using scikit-learn's polynomial features function, which expands the feature set by creating new terms such as squared, cubic, and interaction terms. The challenge is selecting the right polynomial degree, as increasing the degree adds complexity and increases the risk of overfitting. Instead of manually choosing the polynomial degree, pipelines can be designed to test multiple degrees automatically and select the one that provides the best balance between accuracy and generalization. To optimize polynomial regression models, hyperparameter tuning is used to find the best polynomial degree and regularization strength. In machine learning pipelines, this is typically done using grid search or randomized search cross-validation, where different polynomial degrees and regularization parameters, such as those used in ridge or lasso regression, are tested systematically. Cross-validation ensures that the selected polynomial model generalizes well to new data by testing it on different subsets of the dataset. Once the model is trained, the next step is automated model evaluation. In a machine learning pipeline, polynomial regression models are evaluated using performance metrics such as mean squared error, MSE, and R-squared R2. The pipeline compares different polynomial degrees and regularization techniques, selecting the best model based on validation performance. By automating this process, machine learning pipelines reduce human bias in selecting the polynomial degree and help ensure that the final model is both accurate and generalizable. In real-world applications, polynomial regression is often combined with other machine learning techniques. For example, polynomial features can be used as input to linear models, decision trees, or neural networks to improve predictive performance. In financial modeling, polynomial regression can be part of a larger pipeline that includes time series analysis and feature engineering for predicting stock market trends. In engineering, polynomial regression is used alongside simulation-based models to optimize designs and system behaviors. Another key advantage of integrating polynomial regression into machine learning pipelines is scalability. Instead of manually building a regression model for each new dataset, an automated pipeline can process large datasets, test multiple polynomial degrees, and optimize hyperparameters in a streamlined workflow. This is particularly useful in automated machine learning, AutoML, where pipelines are designed to identify the best modeling approach without human intervention. By incorporating polynomial regression into machine learning pipelines, we can automate feature transformation, optimize hyperparameters, and evaluate models efficiently, ensuring that polynomial regression remains a robust tool in predictive modeling. In the next section, we will summarize the key takeaways from polynomial regression, highlighting best practices and common use cases for this powerful technique. Polynomial regression is a powerful tool for modeling nonlinear relationships, extending simple linear regression by introducing higher degree polynomial terms. Throughout this discussion, we have explored its applications, advantages, challenges, and best practices to ensure effective implementation. As we conclude, let's summarize the key takeaways and principles for using polynomial regression successfully. Polynomial regression is particularly useful when data exhibits curved trends that a simple straight line model cannot capture. Unlike linear regression, which assumes a constant rate of change, polynomial regression allows for bends and fluctuations, making it applicable in fields such as finance, engineering, biology, and environmental science. It provides a more flexible approach to understanding data relationships, but with that flexibility comes the challenge of choosing the right polynomial degree. Selecting the appropriate polynomial degree is crucial for model performance. A polynomial that is too simple, low degree, may underfit the data, failing to capture important trends, while a high degree polynomial may overfit, capturing noise rather than the true pattern. Techniques such as cross-validation help find the optimal balance by testing different polynomial degrees and ensuring the model generalizes well to new data. Understanding the role of feature scaling and transformation is essential when working with polynomial regression. Since polynomial features involve raising input values to higher powers, they can become disproportionately large, leading to numerical instability. Standardization and normalization help prevent such issues, ensuring that the model remains stable and interpretable. To improve generalization and prevent overfitting, regularization techniques such as ridge regression L2 and lasso regression L1 are commonly used. Ridge regression penalizes large coefficients, reducing model complexity without removing features, while lasso regression can eliminate less important polynomial terms, simplifying the model while maintaining predictive accuracy. When working with multiple independent variables, polynomial regression extends into multivariate polynomial regression, capturing complex relationships between multiple predictors. However, increasing the number of polynomial terms leads to exponential growth in complexity, requiring careful feature selection and regularization to keep the model interpretable and efficient. Visualization techniques play a key role in assessing polynomial regression models. Plotting regression curves over scatterplots helps determine whether the model captures the trend accurately. Residual plots are useful for diagnosing underfitting or overfitting by analyzing the distribution of errors. For multivariate polynomial regression, contour plots and 3D surface plots help illustrate how multiple variables interact. In modern machine learning, polynomial regression is often integrated into automated pipelines where feature transformation, model selection, and hyperparameter tuning are performed systematically. By combining polynomial regression with cross-validation and automated model evaluation, machine learning pipelines ensure that the best polynomial degree and model complexity are selected without manual trial and error. The key to mastering polynomial regression lies in balancing complexity with interpretability. While a high-degree polynomial can fit data with remarkable precision, it may not generalize well to unseen observations. Best practices include starting with lower-degree polynomials, using cross-validation to test performance, applying regularization techniques when needed, and visualizing results to interpret model behavior effectively. Polynomial regression is a versatile and valuable tool for modeling nonlinear relationships, but its effectiveness depends on thoughtful application and careful tuning. By following these principles, analysts, engineers, and researchers can harness the power of polynomial regression to extract meaningful insights and make accurate predictions in real-world scenarios.